Okay, let's start. Thank you all. I'm Gary Olson from the Department of Informatics, and I've been hosting a visit by our speaker today, Barbara Grosz. She's been here for several days. She actually gave a very interesting talk yesterday about ethical issues in artificial intelligence, and we've recorded it, and it'll be up on the ICS website at some point soon. And if you missed that talk, I would encourage you to look at it because it raises some very important issues about what's going on with artificial intelligence. Barbara herself is one of the leaders in the field of artificial intelligence. She's been working in it for a long, long time. A lot of work in natural language processing, multi-agent collaboration, and so forth. The work she's doing now that she's going to be talking about is especially interesting to us because it has to do with collaboration, how machines and people can work together to make more effective outcomes and so on. And you'll hear more about the details of that. Given that she's a leader in the field of artificial intelligence, of course, she's been widely recognized. She's in 2009, she won the ACM AAAI Alan Newell Award for her work in artificial intelligence, and just a couple years ago, she won the ICHKAI Award for research excellence in artificial intelligence. So she's a very highly honored and respected researcher in this area. She's members of all kinds of honorary societies, ACM Fellow, but all kinds of others as well, not surprising. But I think you'll find what she's doing now is extremely interesting, so I'll let you hear from Barbara.
Thank you, Gary, very much. Thanks for that lovely introduction and for inviting me here. It is a very exciting time for the field of artificial intelligence. I would say the most exciting time since I started in it many decades ago. AI is out in the world in a way I never imagined it would be. So I want to take this opportunity to reflect on the state of the field and its future, as well as to look at the research that I did over the last several decades, winding up talking about my current work in healthcare coordination. Let me begin with 2 points on the title slide. The Turing Test, Turing's idea was to ask a philosophical question in an operational way. He never meant this really as a measure of a field, although people have taken it that way, and you'll see that I think that's a mistake. The Smart Partners Challenge, which I will elaborate on in a few minutes, is in fact not a test in the same sense as the Turing Test, and it is actually meant to push us to build systems of a certain sort. I want to point out that the us in the title is both to highlight that it's us, human beings, that they need to work with, and that I'm interested in getting them to work in groups and with groups of people. So both as members of groups, as team members, and also to support groups of people. This is one of my favorite quotes from Turing's 1950 Mind paper. And since this is now a computer science and informatics audience, I would like to ask the question I always ask at this point. How many people have read that paper? Gosh, how many of you are computer science students? Gosh, okay, so you have to read the paper, the whole paper, not just find a quote or ask a question about it on Google. You cannot be a computer scientist unless you've read this paper. You will discover that things you think are brand new this year, actually Alan Turing thought of in 1950. It's amazing, and not just in artificial intelligence, but in computer architecture, in computational theories, in theory of computation, and so on. So really, to be a computer scientist, you must read this paper. So most people know about Turing's prediction about what we call the Turing Test, but he called the imitation game. That prediction, that is, that we would have systems that could in fact participate in that test setting and do well, did not come true by the year 2000. Actually, he predicts in the paper that it'll take 50 years, and a radio broadcast somewhat later, he thought it might take 100 years. So he still has time. But this prediction has come true. People do now speak about computer systems as thinking. And they, unfortunately, what they often say is, what was it thinking? And they seem not to be intelligent in the depth in which we are intelligent. So a few years ago, when there were many celebrations of the 100th anniversary of Alan Turing's birth, I was asked to speak at one of these symposia, and I thought, what can I say that's new? Some books have been written, movies have been done on Alan Turing's life, and I decided to think about what question Alan Turing might ask now, were he here. Because the question that he asked in his paper was very much a question of his time. There were these powerful machines to their mind. They took up rooms bigger than this and were less powerful than your smartphone. But people were wondering, they were essential to the World War II effort, both here and in Britain. If they were so powerful, could they think? And Turing meant, I think, as we think, that's what he meant by being intelligent. And I decided probably he would, and at the time he asked this, he poses this very operational definition. The trend in psychology was behavioral. So he really fit in his time. And I think nobody knows what he would ask, or I wouldn't pretend to be able to think like he did. But I think he would ask a different question. And I posed to that first audience that I raised this question, the question I liked. I had hoped at the time that other people would pose questions. And I asked them to do that in the Q&A afterwards, and all they did was ask me about my question. So I hope that some of you will think about what question Turing might pose now. But here's the question that I put forward, and I'm going to go into why I think this is an important question for us. So first you have to imagine the setting. It's not a parlor room setting like Alan Turing had. Instead, we have a situation, like many we have today, in which computer agents and people are working together on a non-trivial task, and it's not a one-shot deal. It's not, is this a dog or a cat? It's over a certain period of time, extended in time, could be days, could be months, like writing a paper with somebody, and it's in an uncertain dynamic environment, which is to say it's in the real world. And the question I posed, it was, can a computer agent behave in such a way over this long period of time that people on the team won't notice that it's not human or think it's stupid? And this is not true of any computer system we have now, I want to say that, except for systems that do very, very simple tasks. So I want to highlight that the not noticed doesn't mean that the system is indistinguishable from people. Obviously, physically it wouldn't. Well, Westworld fans aside, physically we hope that it will look different, expect that it will look different from people. But that its behavior is so fluent that we don't stop and think, why did it do that? Or ask, as many people do now, what was it thinking? So it's okay to know that it's a machine, but it has to behave reasonably. Also, by the way, Turing's wasn't trying to get indistinguishability from people, just a footnote. So that's the challenge that I've posed to the AI community. And let me try and give you some background for why before I turn to look at some of my work that actually aims and has over a while aimed at this. First let me set AI in the context of much of the alarmist reports that are in the papers, but also to point out that Turing's conjecture about building a machine that could think, and his fascination with this philosophical question was not in a vacuum. For centuries, going back at least to the 1500s with the Golem of Prague, people have wondered if there could be a man-created agent of some sort, this android, that would think and act like people. And there were mechanical androids in the 18th century. And they kind of, this kind of literature and these stories, which include not just the Golem, but also Frankenstein and more recently Ex Machina. But Frankenstein and the Golem really provided a foundation, along with Descartes, for Turing to ask his question. So now we have AI technology entering the world in abundance. Right? And there are all of these fantasies, like we'll be able to ride in our cars. I don't know why she's in a driver's seat, because she's looking at her laptop. We won't have to pay any attention to what the car is doing. It will drive itself. And then also nightmares. By the way, the nightmares are mostly a phenomenon of the West. In Japan, robots are thought to be cute and cuddly. So we can also ask about our literature and their literature and why we always go for the nightmares, but that is not what I'm going to talk about. So what I would like to argue is that if you want to get beyond the physical focus and you want to get beyond this kind of science fiction of machines gone mad, and you want to think about realizing intelligent behavior in the world, then you really have to focus on augmenting human intelligence and not replacing it. That is, we have to bring back together people from HCI, which split off from AI, or AI from HCI way back when in the beginning. We really have to bring these together. As I said yesterday in my talk, we know how to replicate human intelligence quite well. It's called children. The problem with them, including all of us in this room, is we have only human intelligence. And we need something better than that. Just look at the world. We need some help. Let's build machines that will help us. And furthermore, you can't ignore people. With few exceptions, computer systems are now in the world with people. And we are who we are, and they should work with us, not force us to change and work against our own cognitive capabilities to work with them. So a major thread of my research, really from the beginning when I worked on systems for teaching that were different from the computer-aided instruction, through my dialogue work, has been to enable us to build systems that work well with and for us. And that really requires intelligence in the machine. So I want to go through 5 reasons that I think this is an important area to focus on. I will say usually when I give this talk, I feel like I'm trying to bring everybody along and I'm fighting a trend. But here I am in a room with Judy and Gary Olson, who have been talking about collaboration just about as long as I have, maybe a little bit longer. So thank you for setting a stage where I don't feel so much an outsider. So let me start with computer use now as opposed to 1950. So this is a picture of what computer users used to look like in the use of a computer in 1950. There is one person in one place with one system. It's kind of like astronomers with telescope time now. You got your time, and then you didn't get your time for another few days. That's really not how it is today. We have many people. They're using a multiplicity of systems, and they're spread all over the world, and they're working at different times. So it's a very, very different setting. In this setting, you just don't. In the setting of today, which we see around 3/4 of this, you just wouldn't think about sitting and asking questions and answers back and forth as the way to think about intelligent behavior. But there are other reasons, and they go to the way we think and where our thinking comes from. So I just want to cite, I'm not going to read quotes that I put up, by the way. I'm counting on you to be able to multitask. That a work that actually goes back many, many decades in psychology and cognitive science, that we as people, our intelligence is rooted in social interaction. So one of the most interesting things to me was to learn about brain science research that shows that children who have no social interaction in their first couple of years, and usually this is either very bad parenting or people children put in very bad orphanages, they have less gray matter. For the rest of their lives, their brains are smaller, and they generate less energy. So if you can get the child out of the bad situation before they're 2, you can correct for this. After that, doesn't happen. Tomasello has argued that we start by cooperating and build language on top of it. Patricia Kuhl has very, very interesting experiments that show that in face-to-face with high social interaction, children learn language. They don't without it. I'll just give you an example of one of her experiments. She's at the University of Washington. She took graduate students there. She took a graduate student there who was a native speaker of Mandarin, and she had her student interacting with first language, only language, English parent, the babies of them. So just for short periods of time, interacting face to face with these babies. In the critical time, I forgot to tell you something important. For those who don't know, we're all born with all the phonemes of all languages in the world. By the time we're a year old, we've lost everything except our native language, unless we're lucky enough to have 2 different languages or 3 being spoken to us. So she took the babies in the critical period between 8 and 12 months. She had this Mandarin speaker interacting with them face to face. They kept the Mandarin phonemes. She showed them videos of this same person doing exactly the same behaviors. They didn't keep them. Okay. The obvious question is what happens if you interact over Skype. She probably has run the experiment now. I just don't know the results. Okay, so that's a second reason is that our intelligence comes from social interaction, and so obviously it plays an important role. The third reason is if you're going to build systems that interact with people, they need to know about the people. And as I argued yesterday, we need to design in both ethics and collaboration from the very beginning. So with apologies for those who were there yesterday, but this is one of my favorite interactions with my smartphone. I ask, where's the nearest gas station? I get a list of 16. I ask which ones are open. Oops. And it asks if I would like it to search the web for the quote, which ones are open. Right. I teach a course on intelligent systems design and ethical challenges. The only requirement for prerequisite is 1 programming course. The first assignment is to find 3 things that the smartphone can't do. It's amazing how easy it is to break this. And how interesting some of the broken things are, by the way. So one of the things I think is really important in understanding where we are is to look at the errors that systems make. And you'll see that if we're not designing for interacting with people, there are many, and there are many that make no sense to people whatsoever. Yesterday I talked about how that gets us to very bad places ethically. I'll just give you an answer here, an example here. So autonomous vehicles are making the news all the time. They're getting better and better and better. There are all sorts of predictions about when they're going to take over. But they have this problem, and the problem is us. So we don't always follow the rules. We don't behave so if the only cars on the road were autonomous vehicles, they would be fine. They would have no trouble. They could communicate with each other. But we haven't yet completely changed the transportation infrastructure here, so we don't drive, only they do. By the way, we probably would have to have separate walkways. Certainly given the way people cross streets in Boston, I think they're better behaved here in California, though you're getting bad, guys, you're getting bad. You better watch out. There are always going to be conditions that designers won't have foreseen because people are not so predictable. More predictable than we think, but not so predictable. So those are all reasons from the system point of view to focus on building systems that could be good team members. But there's another reason, which is it's fun and it's interesting, and there are lots of interesting scientific questions. And there are lots of algorithmic questions, and there are lots of questions about modeling people. There are very important questions about things like going between the two, like what's sometimes called handoffs and sometimes called transfer of control. It's great. People you're on the 5th floor? 4th floor and 5th floor of this building. We need you guys to get together. I hope I got the right floors. Okay. So let me just say that it's not only, that in addition to this, because this allows me to go to dialogue, which I think is one of my favorite topics, but once you open up this idea that you're designing not just a system that's there by itself, but a system that's operating with people in the world, and you open up the idea of teamwork, you can open up new challenges. So here's one example of how teamwork changes what's going on. So we have here a robot that needs to get through a door, but it doesn't know how that door works. So if you don't think about dialogue, then you have to, the robot has to know about all the doors, or you have to design the doors to be ones that the robot knows about. Well, what if the robot could ask the door how it opens? And the door could answer. Well, then you have a simpler question. And this is actually not my example. It's from the AI planning literature to try and simplify the AI planning question, and it's from Paolo Traverso. Okay, so I've mentioned dialogue, and I want to say a little bit about the nature of dialogue, because I know there are many people here interested in natural language processing. This was the first area of research that I did, was to understand how. So I was asked to join an early speech understanding project where people knew about the speech processing, and they knew about syntax and semantics, and they knew that context mattered and dialogue mattered, but they didn't know what that meant. And so I thought, well, that's an interesting problem. Nobody knows what it means. I'll try it. And what I noticed, it was my earliest work in what later became called Wizard of Oz experiments, but my earliest work in looking at how people actually behaved. So this is an example not from me, but from Livia Polanyi, that illustrates that dialogues are not just sequences of questions and answers. They're not just linear structures, but that they're actually structured. And again, apologies for people who saw this yesterday. But most people are told that pronouns, like this word them, are meant to refer to the last thing that was referred to that matches in number and gender. And the interesting thing about this particular example is the last thing that matches this, them, and number and gender is kids. But nobody I know who reads this thinks that it's the kids who are going to be put away. Because actually what happened here is the narration of the story was, John came by and left the groceries, "Stop that, you kids!" And I put them away after he left. So many signals in the language and the intonation that tell you that there's an interruption. But notice, and I think, did anybody here think that them was kids to be put away? No. Okay.
Wait,
So
I did.
You
I
did.
just a little.
Yeah.
Yeah.
So notice
Do you
that
have kids?
But you want to put them away sometimes, right?
But that's a very good point, right? Because it's not that semantically you can't put them away.
Right.
Exactly for the reason you said. But we can read, and actually I had examples from people assembling a piece of equipment that whenever they were successful, these were my early dialogues, people would say, plug it in and see if it works. There was no mention of the whole, it was an air compressor, for half an hour. And nobody ever thought that it was odd. And the scenario was a room full of equipment. Because people understand that we move, just like in programs, we move into one process and back out. Okay. And there are a few slides in this that are especially meant for the graduate students and postdocs in the office, and the audience. This is something Alan Newell used to do this, and it was really important to me as a student. He would pass on his wisdom from the research that he had done. And when I gave my research excellence talk, I decided that I would try to do that, and I've kept these slides. The first piece of work I did was to show that dialogues aren't random sequences of utterances, and then with Julia Hirschberg, work that showed that the intonation, the tunes that we use in our language, were among the signals. So that's the past research. The reflections in my career lessons. So what do I mean that senior gurus are sometimes wrong? When I was still working on this, one of my colleagues, very, very senior colleagues, I was at a research institute, SRI, invited Noam Chomsky, a very famous linguist, to come visit us. And we all went out for lunch at a Chinese restaurant. I can still picture the table. And I was very, very shy at the time. I mean, really shy. I was sort of hiding under the table. I came up for food or something. Anyway, she said at one point, "Barbara, you have to tell Noam what you're working on." I was very traumatized. So I told him, and he said to me, "Very interesting, it will never work." So I thought, okay, that's what you think. You're in Boston, I'm in California, I'm gonna keep trying. And I did. John McCarthy, so a big name in AI, told me people didn't matter. He actually changed his mind toward the end on this. But he said people didn't matter, airplanes don't flap their wings. People matter. Okay. So, I want to look at, I'm now going to shift from that background to looking at the research that I've done subsequently. And I just want to say that when you look at the idea of smart computational partners, there are many, many domains that you can think about. There are many types of teamwork. There are many kinds of theoretical foundations. And as you develop the theory, and this is what I'll talk about briefly, because we've used our theories both as design inspiration, for all three of these, design inspiration, system specification, and as an analytic lens. So here are some of the domains in which you can meet the teamwork challenge. I personally, let me point at this one for a minute. I personally think healthcare and education are among the most important because they're places where the people are an endangered species and we should make sure they don't get eliminated. Writing is something that I know people here have worked on as well. So what are some of the settings? Well, we can think of teams, this is the thing that I started out thinking about, teams that have both people and computer agents on them. And we see this in robot-assisted surgery and in rescue operations. For example, Robin Murphy had her robots in the 9/11 rescue scenes. We can also think about computer support of human teams, and I'm going to talk about that today. And then we can think about autonomous vehicles and semi-autonomous vehicles and crowd work. So I'm going to really talk about the first two today. So that's what I'm going to try and cover in my remaining time. So first I want to talk about foundations. As a part of doing my work on dialogue, I recognized that the AI planning formalisms were not sufficient for dialogue, because after dialogue is two people, not one, and AI planning was all focused on planning courses of action for one. And one of the most important things that I realized early on was what it says here, that you cannot build a system that works all by itself and doesn't know anyone else exists and then patch on collaboration. And you kind of see that in this little cartoon my student found. So I won't have time to go into a lot of detail on this, but I wanted to give you, because I'm going to use it going forward, I wanted to give you the sketch of what we called the shared plans theory. So the idea was multiple agents, they shared in the planning. From the beginning, they built a plan together. They then might work either together or independently, but they would be in contact as needed to make sure the plan evolved right. And you'll notice in blue in this specification are the commitments that need to get made, and in purple some of the ways in which they divide up. So the actual shared plans theory is specified logically, but I've got it here in English. And I'm just laying out what some of the constraints are, the requirements, if you want. This is a specification for an agent to to participate on a team. And an important thing to see here is that teamwork isn't accidental. for each one of the things that I've listed here, each one of these principles, you can construct examples of teamwork falling apart if they're missing that principle. So you need the team members to be committed. They can't just get up and walk away. I'm sure if you're doing course projects, you're aware of this. They have to agree on how they're going to do the work. No good for somebody to decide to paint this room blue and somebody else green, and then they're all tripping all over each other. It's important, by the way, that these decisions can be constantly under revision as the world changes. They have to agree on who's going to do what, but they don't have to agree. Once we divide, this is about delegation or dividing, we don't have to all know the details of what each other is doing. If we tried to do that, we'd all go crazy with knowing too much. Okay? But we do each have to commit to doing our part, and we each have to commit to our partner's success. Okay? So that's really important, because that's where we're meeting our obligations to get things done and not getting in the way of each other. It's hard to build systems that do this, because you have to understand what the other participants are doing. But you don't want to exchange all information about what you're doing. So you're delegating and you're trusting your partners to let you know if they run into trouble or if they find something that can help you. So that's the basic theory. And this was first worked out, Candy Seidner and I did the first sketch of this for dialogue. And then Sari Krause and I elaborated it for not just 2 agents, but N agents. And then we went on to develop it further, and one of my graduate students built a system based on this. So what were my career lessons here? Well, one is that persistence pays off. First of all, when we went from 2 agents to N agents, it turned out to be much, much harder and much more complex. Understanding commitment and what has to be communicated gets much harder. But the second is that, again, there were people who thought we didn't know what we were doing. And I remember very clearly when we first presented this work that John Searle was in the audience, and he said, you have the right idea, but you're doing it the wrong way. He and I still disagree about how to do it. But the AI people in the audience, so I'm not very tall, you might have noticed. There are all these tall guys who worked on planning, and so they came, literally, they patted me on the head, and they said if I would just think harder, I could figure it out how to do it in their formalism. I can only report to you that several of them then went on to design competing theories of collaboration, and they don't look anything at all like they're single agents. So the message to the graduate students, if you have a good idea, just keep at it. Okay, so that's the background. When you have a theoretical framework like this, there are many ways you can use it, and I'm going to talk about 3 of them, and 3 pieces of work that we've done. So the first is this inspiration and a design guide, and this is work that we did a while ago on a system that was to help middle schools that not teaching arithmetic, but teaching statistics to 8th graders. And in Massachusetts, the teachers have 30 or 40 students. They have exploratory software they're working on. Nobody can watch 30 or 40 other people using software. So we built a system that would separate out from the student activities. Right, so you have 8th graders, 12, 13 years old. They have exploratory software. They're supposed to be solving problems. Sometimes they make correct steps. Sometimes they make wrong steps. Sometimes they're just playing around. It turns out it's much harder to do plan recognition in that setting than if you have well-behaved adults. So we had to design new plan recognition algorithms. One of my favorites, so this was for statistics. One of my favorite stories about this idea and the work as it was taken forward by the postdoc, Kobe Gall, working on it, is that he moved this to a chemistry virtual lab setting, and the CMU chemistry professor who was using it gave a talk at a workshop I attended, and he said after watching the plans that came back from the system, He understood how his students were solving problems, and it wasn't the way he thought they were. So really, the idea here is to assist, not to replace the teacher, but to assist the teacher by giving them information about all the students that they couldn't get themselves because there was too much to do. So that's one use. The second use is as system specification, and this is work that my then PhD student Ece Kamar did on interruption management. So just to take a simple example, this is a pre-Waze example. So Waze didn't exist, but you have an agent who is observing you driving home and helping you not just figure out the route, but also figure out when you might go shopping. And the question is, when is it appropriate to interrupt you? So the system sees that you've started out on your route. Notice the probabilities on the arcs. It isn't sure whether you're going home on route A or route B. You know what you're doing. But you shouldn't have to tell the system everything you're doing because we've divided up the work here. But it now notices somehow that there's a traffic jam. It gets a news report. And the question is, should it tell you? And basically, you want it to tell you if the utility of telling you is greater than the cost of telling you. And the question is how much might you compute that? And Ece came up with a new representation, which she called probabilistic recipe trees, where the idea is that you not only, and this is a kind of typical AI and or tree, but you not only have the different possibilities, so at the white nodes, but also the probability of taking them. So in this image, like in this setting, like in the previous one, the agent knows all the possible plans that the person could be taking, but doesn't know which one they're using. And the question is, can they figure out which one well enough to be able to compute the value of information? And she showed how to do it. So that's a second piece of research. And this is meeting the specification. So interruption management, you don't interrupt if you don't have, unlike, these dialog boxes that pop up that say, need to reboot your system, okay? That's not okay. They pop up, your battery's going to run out in 3 hours, okay? No, you could have waited 2 hours and 45 minutes before you told me. The idea here is to not interrupt, to not keep me from getting my job done, right? To be committed to my success means you only interrupt when you have something of value. Okay, so that's the specification. And the third, which I want to talk about, is much more recent work where we've used the theory as an analytic lens. So we started, this is a project in collaboration with Lee Sanders and others in the Complex Primary Care Clinic at Stanford. They take care of children, and this is meant to portray the child growing up over time, which is what happens in the best of cases. These children see 10, 12, or 15, interact with 10, 12, or 15 caregivers. So we have parents and a primary care provider, that's what most of us have. They also might have health aides. They have specialists like neurologists, and I think I have a GI doctor here somewhere. But they also have physical therapists, occupationalists, a lot of people. I'm not going to ask you to raise your hands. I'm just going to say no human being can keep track of 12 or 13 other people and what they're doing. If you think you can, come see me afterwards. Don't raise your hand. You don't want anybody in this room to know you'll get a lot of jobs. And electronic health records do absolutely nothing to help with this, except maybe get in the way. There's an idea in medicine that you should have care plans. This, I don't really mean for you to interpret it. The idea of the care plan is to get everybody on the same page. They agree on what you're trying to do, they agree on the action should be taken, and they agree on who should do it. There's a certain amount of evidence that if you have something like this and it's used, you can provide better care. Here's the problem. They're hardly ever deployed or consulted. I think of them as kind of write-only memories. They used to be on pieces of paper. They're now sometimes in some file. And there's basically no technology support, or has been no technology support for this. This is a situation where the previous kinds of planning doesn't work because you don't have these recipes. When you have all of these different doctors, sorry, Jordan, I'm up here. The interventional radiologist does not know all of the details of what the pathologist or cardiologist or gastroenterologist is trying to do. It's not like the other situations. So you've got, and right now, by the way, they communicate in phone calls and email and so. There's supposedly the oh, looks fun. The PCP is supposed to be the quote quarterback and understand it all. You know, you just can't do it. So good care, the plans would be ever present and would be there, and you would have efficient information sharing. So if the cardiologist got information that was important for the social, and I guess we don't have the physical therapist to know, or the social worker to know, they would get it in a timely manner. If they didn't need to know until the next office visit, they would get it then. And they wouldn't get, as they do now, and they look in the ER, it's just all the information. It's so much they can't find what they want. So as we looked at these teams, we realized they were very different from teams that we had thought about before. First of all, they're flat structure. There's nobody in charge. Nobody tells the doctors what to do. Nobody even tells the therapist what to do. I mean, they prescribe for fixing something, but the physical therapist decides on a plan. They're loosely coupled. So there are points of intersection, but not a lot of them. And the trick is to find the ones that matter. They last for a long time. They're continual. The kid grows and changes. Different people are changing things at different times, and the patient is seeing the caregivers at different times. So they typically see specialists once every 6 months and physical therapists twice a week. Many challenges beyond prior teamwork models, and this is what we're working on now. Right, these are two of my favorite quotes from formative interviews that my student Ofra Amir did in the beginning of the project with parents and caregivers. And you can see that the parents are basically carrying the load of being the integrator or the care coordinator. Sometimes if there's lucky, there's a so-called care coordinator at the hospital, but usually what they're coordinating is the scheduling of appointments and not much else. So this flat structure is putting a burden on parents, and they're also caring for this very sick child. It's also putting a burden on the caregivers, and this top quote is probably my favorite quote in terms of pointing at the necessity of all of this. So one of the questions was to ask the doctors if they had an example when they were missing information that they needed about the patient, and they couldn't find it in the EMR. And notice what the doctor says, there isn't an example when I wasn't missing information. That means we're not getting good care. So you can actually see a way that shared plans tells you, gives you some things that you need for healthcare coordination. So remember, we had consensus on the recipe. So one of the things that we decided that technology could do is to provide support for having the high-level approach available for everybody, for having ways for it to change over time, to support the communication and coordination that you need to meet the commitment, and then, of course, to meet this this information sharing need. And I just want to tell you a little bit about, so that I finish on time, a little bit about the work that Ofra did on her thesis, which was to figure out how to do information sharing in this loosely coupled setting. So no complete plan, that's no complete plan knowledge, extended duration. So the lack of complete plan knowledge is a problem. The extended duration allows for reasoning about collaboration problems, collaboration interactions. And so she designed a new representation called mutual influence potential networks that captures which people in a collaboration are interacting with each other and what objects they're interacting with, and uses the extended duration of the task to actually collect these patterns, understand task dependencies and task allocations. And then she designed an algorithm that reasons about information sharing based on those learned collaboration patterns. So we've, and then the question is, does this actually help? So I'm going to give you a quick tour. This is work that she's just, at the 2016 is her thesis. She's just in the process of writing the journal paper for this. But she basically tested this in a collaborative writing situation. So you have several authors. The information you collect is as somebody completes a session, you look at the change log, you collect the actions that they've done. You build this MIPNets that shows, this is the different authors, Chris and Bob and Alice, and the paragraphs that they're touching. And the arcs get higher weighting the more and more you interact with the other person. Okay, so now you have a new author coming in. You're trying to compute the degree of interest of this author. You have the current MIPNet and the last seen document. You rank the changes, and you give them a highlighted document. Now this looks just like Word or some Google Docs, but only a subset is highlighted, and it's the subset that is thought to be most interesting. So she compared this MIP DOI calculation of what to show people with showing in an experiment, with showing them all edits, which is what the current systems we use do, and with filtering. So she calls this personalized, and with filtering randomly. And I won't be able to show you all of the results, and obviously I wouldn't be telling you if it didn't come out well. But so two big results. One, limiting the number of changes is a lower workload. And so that was true of both random and personalized overall. And the personalized filter were judged more helpful by the participants in the experiment, and they also, as ranked by a second set of subjects, resulted in a higher quality outcome. So it looks like being able to compute what is interesting to people will make a difference. Let me skip that. I come here to my final argument for teamwork and thinking about teamwork, which is finding the right problem is the most important part of research. We hear this from Albert Einstein. By the way, this is also a message for the graduate students and postdocs. Make sure you learn how to find problems. That's the most important thing for your research career. And I just want to say that choosing socially relevant domains can yield new and interesting problems, and keeping people in mind will make your problems more interesting. I won't have time to talk about this, but yesterday I talked about the ethical challenges. So just for those of you who weren't there, this is a Barbie doll that fortunately isn't a bestseller. The doll claims to be your daughter's best friend. Here's an example from the New York Times Magazine report of a sample dialogue. Barbie knows the kid has a sister and asks what something nice is that the sister's done. The child says nothing. Barbie says, "What's the last nice thing your sister did?" Hasn't understood the word nothing. And the dialogue goes on. So you'll have to watch the tape from yesterday to see, but I point out that this kind of inability of a system, which is rooted in not understanding that dialogue isn't a question and an answer, but an ongoing social interaction where you have to think about the people, which means that just having a lot of data isn't enough, isn't just awkward, but raises ethical concerns. So I'll just remind you of the problem I put forward. I would like to see the goal of AI, one of the goals to be that we build systems that make us feel smarter and not dumber, and that work seamlessly with us. And I will leave the last words to Turing, who said we should all be coming up with conjectures. and to John Dunn. Oops. So thank you.
Okay, we have time for a few questions.
Should thank all of these people who worked with me.
Some questions?
Somebody has to have a question.
There's one in the back.
Do you have any suggestions for finding important problems? How can we do it?
It's finding important problems.
Yeah, to work on.
To work on, yeah. Read a lot of papers and figure out what you don't like about what they're doing because it's too small or you don't think they got it right. Go to a lot of talks and don't try to just make, 95% accurate, 96% accurate, but try and fundamentally change what's there. Judy.
I was noticing that your framework about how you're going to get computers to collaborate actually says a lot about what we should tell people up front about how to collaborate, independent of the computers. Because I talk a lot about having a communication covenant up front, but it seemed to have a lot of
Really?
these things in it, not all of them, so I learned a lot about what to put in it.
Thank you. Yeah, this is always my hope, and did I actually have this quote here? I can't remember one of. No, I know. So there's a wonderful. Oh, maybe it is here. Now, there's a wonderful quote of Turing's where he says, we'll learn about how we think by trying to build systems that do it. And so I'm really pleased to hear this, and I would love to talk with you more about it. Because it's, I think that's great. That's all I want to say. And there's a nice compatibility between what we did and what Ed Hutchins has talked about also. So I think that's really important. I thought I saw another hand. Yeah.
Are there any other essential papers you recommend reading, or?
Yeah, so for our work, for our work, it's the papers I put up here, and also you can find them on my website or Ofra's website. And then, it's always really good to look at the references. So when people cite papers, don't just skip that part. Go look at the titles of the papers they're citing, and then skip. So this is what I tell my students here. Look at the reference list, skim the abstract, see if there's something that looks interesting. Then skim the introduction and the conclusions, and you'll find things to read. So there's other work on all of the things I talked about, on dialogue, on intonation, on formalizations for collaboration, which leads to if you want hard problems, decision making in the context of teamwork is much harder than not. And just to give you an example. If somebody offers you, now I never know what the latest rock group is, but if somebody offers you tickets to your favorite music group tonight, and what you were going to do tonight instead was your laundry, that's one decision. If what you were going to do tonight was meet with a project group for a class, it's a very different decision. And the ramifications are different if you decide to go to music, right? So you can see some of the complexities that come up there. Lots of problems in that area that remain to be solved. And also you can talk to Judy Olson and Gary Olson, and they'll give you a lot of problems. They're really good sources. If you're interested in teamwork and collaboration, right? You guys still have problems.
Any other questions? I'm told I'm supposed to announce for those of you who are in CS 200S that the secret word is intelligence. So, Barbara, thank you very much for a really interesting talk.
Thank you.